You can take the stuff home and spend 12 hours and make it beautiful, and you'll still get full credit. I would really rather you not spend an extra 12 hours at home on the lab. Take that time for the lecture part of the course. That's part of the reason why all I want is 3 hours worth of effort. Get the job done, get it written up, get it turned in, and then get back to studying the lecture part of the course. I remember taking physics labs and taking, oh God, the whole weekend to write up the lab. And I finally realized I'm doing this for 1 point. I could have taken the entire weekend for the lecture part, and that's 4 points. That's 4 grade points. So I don't want you to do that. I want you to, you're expected to do 3 hours of effort. That's what I want to see, 3 hours of effort. I don't want you to do more than that. Yes?
So is the lab due at the end of class, or is
Yes,
it due
right
next
at the end
week?
of class,
Right at the
or
end of
whenever you
class.
feel like leaving. Yes?
So these are lab credits counting on the homework you're excited?
The lab credit will be 20% of your score, your overall score. And, oh, and there is one thing, there's one comment on your syllabus that I want to emphasize. Not only will your lab be 20% of your score, but you must pass lab to pass the course. So, you know, I've actually had this happen, ladies and gentlemen. I've had a student who got an absolute A in the lecture part of the course and never did any lab. He said, oh, it's only 20%, so I'll get a B in the course. So like, no, you gotta pass the lab to get your A. So there's a double kind of statement about laboratory. 20% plus you have to pass lab to get your grade in the course. Okay, 15 more minutes. So I'd like to spend a little bit of time. Let me check my notes and make sure that I've covered everything I want to in lab. Yes, I have. There's my suggested data table that we'll be talking about. Back to the theoretical part of the course, back to now chapter 21. We already very briefly mentioned that the 3 forms of heat transfer, and we use these names, conduction, convection, radiation. I think I asked you to associate with the word conduction solid, with convection fluid, and with radiation vacuum. Because when I say conduction of heat, I want you to remember nothing moves but the heat. Convection, when you move heat through convection, you move a heated material. And radiation, you don't necessarily need anything for radiation to pass. Now in conduction, this is a topic very important to most of you because you're engineering majors or science majors. Very important topic. We could imagine an experiment where we have, let's just call it a reservoir at temperature T1, connected by, imagine it perhaps to be a metal rod, a right circular rod like this, to another reservoir at a lower temperature, call it T2, and you know that energy in the form of heat, thermodynamic energy, will be moving through that rod in the form of conduction. Heat will conduct down that rod. Nothing will move but the heat energy itself. And it would be reasonable to assume that the heat, which I think he uses capital H, yes, capital H to represent the quantity of heat that is moving, energy per unit time, is related to the cross-sectional area of the rod connecting. If the rod is twice the area, twice as much will pass. If the rod is 3 times in cross-sectional area, it will be 3 times as much heat will pass. So the heat must be proportional to the area of the rod connecting the 2 reservoirs. It must be, excuse me, proportional to the temperature difference. If these 2 temperatures are very close to each other, the heat flow is very small. If the 2 temperatures are very wide, a huge difference in temperature, the heat flow must be high. So I will put down dt dx, where x measures the distance along the rod, x, like that. And I left a space in between because there has to be one more thing. Thinking about your material science laboratory, there must be one more thing related to the heat flow. What? Yes?
The medium of the material.
The medium of the material. What the material is made of. Everybody knows that metals conduct heat very, very well. If that rod is made of wood, heat won't move down there very well at all. So made of styrofoam, it'll hardly move at all. So there is a constant which he calls K, the coefficient of thermal conductivity. And this will describe how heat transfers. Now, if you were, for example, designing this building, you would be very interested about how much heat goes through that wall right there. So, we need to know the thickness of the wall, the two temperature differences, like how warm do we want it in here, how cold will it be on the coldest day. What is the surface area of the concrete? And what's the coefficient of thermal conductivity for concrete? And we can calculate how much energy goes through the wall. Then, of course, you have to do glass and add that in. And you have to do, I don't know what that is, it's metal and wooden door, so you have to add that in. So to determine how much heat goes out that wall, all you have to do is to get the temperature difference. In other words, let's say we like it 70 degrees in here. On those frigid days when here in Ventura County it drops way down to 50.
We just don't have sympathy for people in Wisconsin, do we?
So it's 50 degrees out there, 70 degrees in here. The delta T is 20 degrees Fahrenheit. The X is the thickness of the wall, I don't know, about 1 foot. K for concrete and A the surface area. That's one way of using this thing, to determine what is the heat flow into the room, what's the necessary heat flow into the room to account for the heat flow lost out that wall to keep it at a comfortable temperature. Or, more commonly now, building electronic components, very often you're putting heat into the system and it will melt itself, it will destroy itself if you don't tap the heat off, if you don't sap the heat off. So they make heat sinks made of metal that attach right to the hottest part of the electronic device. How big does it have to be? What metal? How far does it have to dissipate? What's the temperature here? What is the highest temperature I can tolerate here? What is the temperature at which it will be rejecting this heat? And you can calculate that sort of thing. This is very much an engineering topic, and of course, because it is so and important in construction, they have decided that they can, summarize things very nicely by simply first rewriting it like this: H equals K A delta T over delta X. So what have we done here? Now we're talking about real measurable distances across the conducting surface and real measurable temperature differences. No longer are we into differential comments of the flow through a rock. Then you can summarize it simply by saying that delta T, that the allowed temperature difference, or the measured temperature difference, would be H times delta X over Ka, and then summarize that as R, the R value, which kind of summarizes the behaviors of things like walls, as long as you know the surface area of the wall you're talking about. Or better yet, if you get rid of the area, if you say R times A is R factor, which is delta X over K, this thing called the R factor evaluates the construction material. If any of you have worked construction, you probably know that there are now requirements. If you're going to build a house or a building like this or something like, your plans must be submitted and the walls must have a certain R factor, which just simply measures the thermal resistance of the walls. And I don't remember, have you worked construction, do you recall the R factor requirement here in Southern California? Say it again? R40 for the ceilings is something like R13 for the walls. 15 to 13. Yeah. So the down this the county board, they have R factor requirements, and I always find it interesting that Southern California is, I think you're right, maybe 15 R factor, exterior walls, and R factor of 40 in the ceiling. When I was in Seattle, I think it was R factor 40 in the walls and R factor 60 in the ceiling, and that's just Seattle. So each area has its own R factors. Very important topic, especially in construction, yes.
Well, the problem I don't understand is if T2 is significantly greater than T1 and the delta X is really small, then as the heat is transferring, won't the material expand, say if it's like metal? So how do we factor that into this? And
That's an interesting question when it comes to something like concrete. And they do have to consider that, except that the change is on the order of 10 to the minus 6. Remember that, the coefficients of linear
Well,
expansion?
that's why I mean it's important for very small things.
For very small things, especially the electronic component part that I was talking about, yeah, you have to take that into account, if for nothing else, for physical reasons, in the circuit board itself.
But would you use the final delta X or the initial delta X, or would you use like a differential delta X?
You know, if you really want to be careful, you don't have to be this careful. If you really want to be careful about it, you would have to manufacture it at a certain temperature and then say, assume this is at that temperature, assume that is at that temperature, and you would have a difference in size. But as far as the heat flow is concerned, the heat flow won't be any faster than the smallest area. Even though the hot side gets really, really big, even if you made the hot side really big, the flow is for the smallest area or the lowest temperature. But again, keep in mind, we're talking 10 to the minus 6 for the coefficient of linear expansion. Okay, so I just wanted to mention that topic. It's a very important one. We also mentioned convection, and yes,
So if you give us a problem where something is connected by like a conical shape, then if we have the opening of the cone versus the larger opening of the cone, then it would only be the smaller opening of the cone would be that cross-sectional area we would use.
the heat flowing here must equal the heat flowing here.
Yeah.
But this is going to be a certain heat over a certain area, so there's going to be more heat over lesser area, and this is going to be lesser heat over a larger area. So you're asking me about something I'm about to talk about, and that is heat flux. What is the flux over these areas? Okay. Let me see if I can get to that. So convection. We mentioned convection before, and my main comment about convection is it's extremely important, extremely complex. Convection always depends on many specific parameters of the individual system that you're analyzing. And where I see convection as a major issue is in meteorology. This whole planet, the weather on this planet is nothing more than huge convection currents. And as you're probably well aware, they've been spending decades, at least 5 decades, trying to refine a computer model that will model the convective system of this planet. That's typical when you're dealing with convection. You have to make computer models, and it takes years or sometimes decades to get a computer model. There's no specific law of convection where you can say they behave like heat flux. You have to know the details of the fluid and the temperatures and the shape and the heating element and the cooling element, and then you try to build a computer model. They're getting pretty good at it in meteorology. I have to stop for just a moment and say, you know, they're getting pretty darn good at it. I don't know if you're aware of this, but if you evaluate the meteorologists, they're accurate about 92% of the time, which is a good solid A in a college class, isn't it? I'm surprised because when I first started teaching, I thought they were doing good. They were 80% 30 years ago. 30 years ago, the meteorologists were accurate. 80%, they've improved, I think, dramatically. They've gotten up to 92%. Will they ever make 100? I don't know. But that's where we talk about convection. You see issues related to convection. As you recall, my issue in this class and our Wednesday lecture is going to be